In this video, we'll be going over the bottom-up approach of unique paths 2. Let's go over the thought process. So we'll be converting the memorization approach to a bottom-up approach. Now, where do we start? In the memorization approach, we have cached the current row and column with the number of the unique paths. This means we can create a 2D matrix paths to keep track of the unique paths for all combinations RC. To keep track of the unique paths for all combinations of RC. Now it asks itself, what are the default values inside the paths matrix? So when RC is out of bound or contains a 1, which means it's an obstacle, then the number of paths will be equal to 0. Then when RC is at the bottom right corner, then we have found one possible path. The number of paths will be equal to 1. Let's go over the pseudocode. So we're going to create a 2D matrix, paths, to keep track of the unique path for all combinations of RC. Then we're going to iterate through from n-1, which is the total number of rows, to 0. It's going to denote it as R. Oh, this means the last row. Then we're going to iterate through from n-1, the last column, to 0, denoted as C. Then we'll first check if RC is at the bottom right corner. Then we can set, actually before that, if obstacle RC, if the current cell contains a 1, that means this obstacle here is equal to 1, then we want to continue to the next iteration, which means the path of the RC of the current cell is equal to 0. So we can just continue to the next iteration because the default value inside the paths matrix are zeros. Then if RC is at the bottom right corner, we have found one possible path, so we can place 1 at paths RC. And we can continue to the next iteration. Then if R is not at the last row, this means we can move downward. So the robot can move downward. So we're going to increment the current number of paths by the number of paths of moving downward by paths R plus 1, which is moving downward. Then if C is not at the last row, last column, then we can move rightward. So we're going to increment paths by the number of paths of moving rightward. So R plus 1. Then we can return the paths starting from the 0, 0, which is the top left corner, the initial starting position of our robot. Now let's go over the time and space complexity. So time complexity is Mn, where M and N are the number of rows and columns. And then this is just a nested for loop. And our space complexity is also Mn because of the path matrix. Now let's go over the code. So let's first create two variables to keep track of the number of rows and columns, which are M and N. Then we're going to create our paths matrix. Then we're going to iterate through from the last row to 0. So R is equal to n-1 to 0. And then we're going to iterate through from the last column to 0. Then if the current cell contains an obstacle, the number of paths is equal to 0, so we can continue to the next iteration. If R is equal to n-1 and C goes to n-1, that means we're at the bottom right corner So the number of paths is going to be equal to 1. So paths RC is equal to 1. Then we're going to continue to the next iteration. Then if R is not equal to n minus 1, that means we can move downward. So the number of paths at the current cell will be incremented by the number of paths of moving downward. Then if C is not equal to n minus 1, that means we can still move rightward. So we increment the number of paths by the number of paths moving rightward. And then return the number of paths starting from the top left corner, our initial starting position of a robot. Let me know if any questions in the comment section below.